our next speaker of the early afternoon session is Ling, who will tell us about top-down constraints on the symmetry, the topological field theory of supergravity.
Thank you. Thank you. Let me also start by thanking the organizers for organizing this conference and giving me the opportunity to present some work I did with Dawi Gould and Evita Sabag from Oxford. And it's an attempt to scrutinize a concept from the generalized symmetry community called the SymTFT from the Swampland perspective. And the basic kind of models we have in mind are supergravity theories that from recent years underlie a principle that's called string universality or the string lamppost principle. And by that, I mean that once we accept that with enough supersymmetry, in this case 16 supercharges, a supergravity theory is in some sense completely specified by just some local gauge data, then it looks from a bottom-up perspective somewhat peculiar that within the string landscape, the data that you, from an EFT perspective, typically would think to be as some arbitrary but freely choosable set of possibilities, that the actually realized models in the landscape are very constrained. The type of non-abelian algebras in these high dimensions from string compactifications is very limited, and also the patterns of ranks of these gauge groups in different dimensions are not arbitrarily chosen. And over the last 10 or so years, we've actually understood that this is not at all a shortcoming of string theory in realizing and constructing effective field theories, but instead is a reflection of more subtle anomaly constraints or some Swampland arguments, which essentially eliminates all the possibilities that are not realized in the landscape, and thus giving rise to this idea of string universality, by which mean that at least with enough supersymmetry, all the possible consistent effective field theories are realized in string theory. So once we have addressed the gauge algebra, the next sort of obvious question is, what about the gauge group? And from a more formal perspective, this question is actually also relevant in the sense that if I just tell you an effective field theory using the data of its algebra, then what I'm constructing is not a proper quantum field theory in the sense that the partition function of that quantum theory is really a vector, which you should be thinking of as a state in the Hilbert space of a one-dimensional higher theory to which that d-dimensional theory is the boundary of. That's the notion of relative theory. So in order to really get a genuinely d-dimensional quantum field theory, it is absolutely necessary to pick a global structure, and in this case for just ordinary gauge symmetries, it amounts to picking a gauge group. Now, of course, going back to the set of string realized models, we can ask again, what are the possibilities for these gauge groups? And we again find some curious patterns that a priori does not seem to be motivated by any underlying physical principle. For example, in 10 dimensions, we know that the spin 32 heterotic string really has a Z2 quotient, and there is no version that has just a simply connected gauge symmetry. And likewise, in lower dimensions, for example, in 9D, there is no simply connected maximal rank SU18 example. And this kind of pattern in the modern language of generalized symmetries can be recast in this notion of the symmetry TFT, which I will spend the next few minutes explaining. But using that framework, then it's natural to revisit these patterns we encounter in the landscape and ask ourselves, can we explain these patterns that we find, or at least quantify them in some concise mathematical way using the symmetry TFT? So for the rest of the talk, I will first explain this notion of the SymTFT of a supergravity theory, and then present some constraints that we can derive from some geometric constructions of these these supergravity theories, which then we formulate using SymTFT in a bottom-up language. Okay, so let me start by first giving a brief introduction to the symmetry TFT. And its basic idea is to separate dynamical degrees of freedom, say your gauge fields, your massless matter fields, from the topological degrees of freedom, which in this modern language of generalized symmetries is objects that generalize global symmetries. That generate global symmetries. And the separation roughly proceeds in the following way. The local massless degrees of freedom are specified, are confined to a d-dimensional space-time, which we call the physical boundary. And the topological degrees of freedom extend into a one dimension higher, which is this high dimensional theory to which the boundary is relative to. And in order to produce a d-dimensional quantum field theory, we need to pick some boundary conditions on the other side of that interval and reduce that interval. And in that process, we automatically specify the global symmetry structure of the d-dimensional QFT along with its charge operators and the global structure in the context of gauge theories. So the examples I would like you to have in mind for the rest of the talk is to imagine what we need to do in order to obtain, for example, Wilson lines that are the electrically charged objects under a one-form symmetry. In this context, the topological operators in this high-dimensional bulk will be two-dimensional surfaces, and if I orient them on the physical, on the symmetry side of the boundary, so where I specify the boundary conditions in such a way that they have to end perpendicular, then after that interval compactification, I'm led to this d-dimensional quantum field theory where I have genuine line operators, the things that are charged under one-form symmetry. And I want to contrast this to the situation where I want to imagine now picking the magnetic version, i.e. A theory where I only have the dual magnetic higher form symmetry. And in the SymTFT picture, what I have to do is basically change the boundary conditions on this symmetry side to now allow these two-dimensional topological defects to end parallel to that surface. And after interval compactification, these parallel ending configurations will give me the Gukov-Witten operator that generate the magnetic symmetry, as well as achieving or making the Wilson lines that we had on the physical side non-genuine, i.e. making them no longer making them into non-genuine operators, so they're not gauge invariant object charged under some one-form symmetry. Okay, so then having with this sort of brief introduction in mind, what do I mean by the symmetry TFT of a supergravity theory? So naively, a gravity theory should not have any global symmetries, but since we're working from a bottom-up perspective where we think of describing any quantum gravity theory using some effective field theory, then in this class of models of supergravity with 16 supercharges, the data that I'm specifying are just a bunch of vector multiplets, which either come from the gravity multiplet, and that gives me some abelian gauge factors, or some non-abelian gauge factors with only adjoint matter. So if I just give you this data from as a gauge theory data, then you would immediately conclude that in principle I have the choice of inserting Wilson and 't Hooft operators, and without any further specification, I can insert all of them, which of course in a totality would violate Dirac quantization, and that's one way to see that without specifying the global structure, I do not have a proper d-dimensional quantum field theory. So in order to avoid that issue, we need to pick a global form of the gauge sector, and that amounts to specify the boundary conditions of this particular set of defects that violate the Dirac quantization. And that particular symmetry TFT is what I refer to in this talk by the symmetry TFT of supergravity theory. Right, so just the set of gauge fields that I specify in the beginning to tell you what supergravity theory I'm working with naturally gives rise to this defect group with an associated SymTFT. And then from the Swampland philosophy, it's a natural question to ask, if this is a gauge sector of a quantum gravity theory, then what are the restrictions on the choice of boundary conditions, i.e. the choice that specifies for me the global structure of the gauge group that comes from coupling this gauge sector to gravity? And the question would be, are there any restrictions? And as I hopefully motivated to you earlier, these landscape observations suggest that the answer to that question should be yes. So our task is to at least quantify how these restrictions look like. So one set of these restrictions come from a kind of anomaly arguments that exists between the one-form symmetry and the instanton symmetry. And in the specific case of these high enough supersymmetric field theories, this can be recast into an anomaly term which is basically involving the field strength of the instanton U1 and the gauge potential for the background gauge field of the one-form symmetry. And it's an anomaly because this coefficient alpha here is in general fractional. Now, to apply this to the context of non-trivial gauge group, global gauge group structures in the context of supergravity, we simply observe that one way to specify this non-simply connected gauge group is to imagine starting with the simply connected gauge group and gauge the one-form symmetry. And at the same time, in the context of 6 supercharges, the U1 instanton symmetry is actually also a gauge symmetry. So having a mixed anomaly between two fields which are associated with gauge symmetries produces a obstruction to the gauging, or would somehow break these gauge symmetries. So in order to have that non-trivial gauge group, I need to make sure that this anomaly is absent. And in the SymTFT language, this anomaly, because it's an additional term in the Lagrangian for the topological field theory, it will just modify the boundary conditions in such a way that you cannot now pick arbitrary boundary conditions for this electric one-form symmetric background, but only a certain subset of them. And that will basically reproduce this, this condition of anomaly free in this, in this gauging language. But having said that, this kind of anomaly argument is always only a necessary condition, right? Because there's a trivial way of making this anomaly go away just by setting or imposing that these fields always are turned off in some sense. So in some sense, the choice where I'm not quotienting my gauge group by any subgroup would always be a consistent choice from this perspective of the anomaly. But as we've seen earlier, for example, in antiheterotic, this is not a choice that's realized in the landscape. So how do we exclude these possibilities? So this brings me to the next part, which is to now look a bit more closely to how we extract the symmetry TFT from geometric constructions in string theory. And actually, the SymTFT is naturally incorporated in the geometric engineering of non-gravitational quantum field theories, because when we compactify or reduce the high-dimensional theory on a non-compact space, we not only have massless dynamical degrees of freedom associated to some local compact features of the geometry, but also a degrees of freedom associated with the asymptotic boundary of that non-compact space. And by wrapping the branes that we have from string theory or M theory on these cycles in the boundary, we naturally get topological objects that correspond to the symmetry generators of the quantum field theory, or I should say of this relative quantum field theory. Because now I have to still specify the boundary conditions for the p-form gauge fields of string theory on that asymptotic boundary. And a consistent choice of these boundary conditions, which precisely is the boundary conditions in the SymTFT picture, amounts to picking a mutually local choice of branes, which wrap now the non-compact cycles that extend from the local singularity or any compact cycles all the way to the asymptotic boundary. So for the rest of the talk, I will focus on this particular example of M theory compactified on complex Kähler surfaces with some ADE singularities. So I'm ending up with a 7-dimensional super Yang-Mills theory whose SymTFT the reduction of M theory on the boundary is a A-dimensional BF theory whose gauge group is just given by the first homology group of the boundary, which happens to be the center of the simply connected Lie group associated with that Lie algebra. And in this context, the Wilson and 't Hooft operators, so the charge objects under the electric and magnetic higher form symmetries, will arise from M2 and M5 branes wrapped on these relative 2 cycles. And the symmetry generators for these 1 form and 4 form symmetries will come from now M5 or M2 branes wrapped on just the cycles at the boundary. And again, these allowed boundary conditions, which limits my set of charge operators to satisfy the Dirac quantization, are just again a set, just restricting the set of M2 and M5 branes that wrap the relative 2 cycles to a subset which do not link on the boundary. And as a bonus of this construction, we can also obtain this set anomaly term earlier from the dimensional reduction of the Chern-Simons term of M theory, which in this geometric context corresponds to some Chern-Simons invariant on this asymptotic 3 manifold. Okay, so this is the setting when we have a non-compact internal space in the compactification. Of course, when we want to realize supergravity theories, then typically we're compactified on a compact manifold, which does not have any boundary. So it's a immediate question is, how the hell am I supposed to associate an SymTFT with a compact internal manifold? And for restricting ourselves still to this case of M theory on 4 manifolds, the set of compact 4 manifolds, i.e. K3 surfaces, I can think of as being glued together from a set of local ADE singularities, which I excise from the K3, that will leave me with a smooth surface with some points removed. And the complete K3 I can obtain by just gluing these 2 patches along some identification in their common boundary. And in this separation of the K3 geometry, I now naturally have a sector associated to the abelian gauge factors coming from this non-singular patch and the non-abelian ADE gauge factors coming from these local singularities. And if we look at this intermediate step where we really separate this decomposition into a disjoint union before we glue them together along the boundary, then we have a natural candidate for the SymTFT of this U1 times non-abelian gauge algebra, because we have a manifold with a boundary, which is just the disjoint union of these 2 boundary of these 2 pieces, on which we can reduce M theory to get this topological theory in 1 dimension higher. And there's some geometric subtlety coming from the fact that this the non-singular patch in this decomposition of the K3 always has some non-trivial compact 1 cycles in the interior. So that actually results in a slightly smaller set of topological operators on the abelian side for which I have to pick a boundary condition. And that smaller subgroup you can think of as basically the defect group for the U1 to the R gauge sector, because these are just what remains after including certain heavy U1 charge states coming from that homology group. So with that small, subtle but important detail in mind, now we have this natural SymTFT candidate of the supergravity theory, which is the A-dimensional BF theory with a gauge group associated with the center of the non-abelian factor and this discrete group to which I have screened my continuous U1 symmetries to using some massive states. So this gives me a set of mutually non-local charges, electric and magnetic charges, labeled by this discrete group. Okay, so a priori, if I just give you this as a bottom-up FEFT data, again, you have many choices of possible global structures that are consistent with both the Dirac quantization and this anomaly argument, anomaly condition that I presented earlier. In particular, regardless of anything else, this choice where the set of electric, i.e. M2 branes that wrap with the relative cycles, I can always pick to be just a trivial set, right? So I would always just end up with a trivial quotient that would be consistent with all these considerations. But because that whole setup is artificially chopped up into two disjoint pieces, comes from actually a compact K3, there is a preferred or a physically distinguished set of relative two cycles on each patches, which are those that glue together along this boundary to give you a compact two cycle in the full K3. Right? If I just look at the two patches separately, I could a priori choose to wrap M2 and M5 branes on pairs of relative cycles as long as I make sure they are mutually local. But because they come from this gluing along a common boundary into a compact geometry, I actually have to wrap M2 and M5 branes on the same pairs of relative cycles in each patch, which glue together to a compact cycle. So that simple argument immediately tells you that what you briefed before from a bottom up would expect to be, up to this anomaly condition, some freedom in choosing electric and magnetic charge states. In the compact setting, the discrete group that characterize them have to be the same. Just because in this geometry there is only one kind of two cycles that must be wrapped by M2 and M5. So now we can go and distill some more properties about what kind of subgroups in this in this finite center satisfy this property. So I will just summarize the salient features from the more involved geometric analysis. The first one is I just want to point out again that this, the U1 gauge sector in this gauge theory comes with this discrete defect group. So I've already screened some of the center symmetries of the U1 to this discrete subgroup, which by this geometric consideration actually has to be also a subgroup of the center of the non-abelian group. And that just came from the fact that because we're gluing both the abelian and the non-abelian sector along the common boundary in the geometry. And then from the Mayer-Vittori sequence that I'm associating to this gluing, I can extract that the subgroup Z, by which I'm quotienting the simply connected gauge group, has a non-abelian part and this extra part, with the non-abelian part just sitting entirely in the center of the ADE group, and this extra piece actually being a diagonal subgroup of this product. And a diagonal because the ZAB factor is a subgroup of the first factor. So that comes from carefully looking at the Mayer-Vittori sequence. And then if we further realize that these boundary one cycles came from compact two cycles in a K3, which has to satisfy certain integrality and moreover even intersection properties, then we can conclude that the subgroup associated with these two choices of one cycles actually have integral transaminds invariants on the boundary components. So I don't want to bore you with the details in this abstract mathematical setting. Let me instead directly translate this into a physics context, which allows you to interpret all this geometry from a bottom-up fashion without ever needing to refer into geometry. So the first part about this ZNA factor just translates into the fact that if I take the quotient of the non-abelian gauge group by it, I end up with a non-simply connected non-abelian gauge group that is free of this anomaly because the transaminds invariant is integer. Now, in this bottom-up perspective, I a priori do not have access to how exactly I'm screening my U1. So you might think that now I've lost some leverage on how to describe the physics of this model. But in fact, you can turn this around and just impose that whatever the screening achieves, it screens it into the U1 factors into a discrete group, which has to fit inside of the non-abelian gauge group center, and in such a way that this diagonal subgroup is also anomaly-free. And you can recast these two conditions in such a way that this subgroup Z inside of this product group is a maximal subgroup, so its order is the square root of the order of this discrete group, which also has to be anomaly-free. So that now, you have to basically make sure that you can screen your U1 factors to such a subgroup, ZAB, such that then inside of this product you further find this anomaly-free maximal subgroup Z. And this is the condition that you find for things that come from geometry. So now in the Swampland spirit, let's just flip things around and propose that for any given non-abelian gauge algebra, whenever I can find a screening of the U1 sectors to such a discrete subgroup that satisfies all these conditions, then that particular global gauge group is consistent and can be realized in string theory. And indeed, in all the examples we have, that condition alone is necessary and sufficient to find a string embedding. So before I come to the examples, I just want to make a statement about the validity in higher than 7 dimensions, because all these geometric arguments come from, I just summarized this briefly. All these geometric arguments come from M theory, and if we connect this to the heterotic picture, then we actually see these geometric properties have a natural description in terms of the momentum lattice of the heterotic compactification of the torus, and all of these anomaly-free conditions translate into known properties that guarantee that the heterotic description has a properly defined gauge group. So in view of time, I skipped these examples. I just highlight the simplest case in 10D, where you can use this criterion to rule out the simply connected spin 32, because that does not have a mixed boundary condition. Right? You need to go to spin 32 mod Z2 to get this maximally mixed in between electric and magnetic pairing. And there are many more examples. In particular, if you entertain the thought of an SU3 times SU2, to make that thing compatible with the condition, you would at least need 3 U1 factors. But again, that's, since Senna model and so forth is not really 6 supercharges, let's not dwell on this for too long. Okay, so let me briefly summarize. The curious pattern that we found in the gauge group topology for supergravity can be translated into a condition on the SymTFT that characterizes the choice of these groups structures in terms of what we call this maximally mixed boundary condition. And it can be equivalently formulated into picking a subgroup of the one-form symmetry, which is maximal and is free of the mixed anomaly with the instant on U1. So one clear next step is to include what I've neglected so far, namely all settings with frozen singularities and in the heterotic context, twisted boundary conditions. This will hopefully be addressed in some upcoming work. There's also another perspective about 2B that I will skip now, which, however, is to motivate the idea that even though I have provided for you a way to characterize the consistency of these gauge groups, I did not provide a genuinely bottom explanation for why this maximally mixed boundary condition has to hold. In this setting of type 2B, there is an a posteriori explanation using some mixed anomaly, but we have not found such an anomaly so far. And I hope there will be progress in due time, and please stay tuned, and thank you for your attention.